So you see that the mass is suspended and completely immersed in this liquid. It is not touching the base of the beaker, and it is not meant to touch the base. This is how you would know that the system is in equilibrium. You notice the ruler is not falling, everything is stable, right? But then the mass is not touching the base. I repeat, the mass is not touching the base of the beaker. It's suspended. You can see it lifted there, but completely immersed in the liquid. The water is up to this level, as you can see. All right, so this shows that the system is balanced. This experiment is when the mass M is placed at 10 centimeter mark. You can take a look at the 10 centimeter mark of the meter rule. All right, you can see that. So take note, the main point here is that for this to be balanced, right, the mass that is immersed totally in the water should not touch the base of the beaker. All right, in fact, it should not even touch any side of that beaker. It's just meant to be suspended in the water like that. Then you can now say that, yeah, it is balanced, that the system is balanced. Now all we have to do is to read our Y2. I'm going to take this to the point where you would see. So we read our Y2. Y2 is the distance from the pivot point, which is 50 centimeter, kept constant throughout the experiment, up to the point where the 100-gram mass was used to balance. I actually adjusted this mass, and looking at it, it is at the 67.0 point. You can see the thread, all right, 67.0. So to get our Y2, all we have to do is to take the difference. We subtract 50 from 67. That's simply the distance from this point where the mass of 100 grams is suspended to the pivot point. If you work on 67 minus 50, that's going to give you 17, right? So for Y2 is going to be 17. Y2 is going to be 17 centimeter. So this is what you are expected to do when the mass M is completely immersed in the fluid. This will take us to the second experiment, all right? It's going to take us to the second experiment. And remember, in the second experiment, we are to adjust this mass M, all right? This unknown mass M to the 15 centimeter mark. So you follow along. I'm going to adjust it, okay? Now, I have adjusted it to the 15 centimeter mark. And you notice that I'm holding this ruler. If I remove my hand, this is going to be funny. You see, it's raising up. Just watch that water. You notice that the mass is lifting up, and of course, the ruler is falling towards the right side, as you can see that. Watch. All right. So this simply tells us that this system is no longer in equilibrium, and the reason is simple. Remember, in the first experiment, I placed that the 100-gram mass balanced at 67.0, that's simply 67, where we got Y2 to be 67 minus 50, giving us 17. But then, this time around, right, we are told to adjust the mass M, which is totally immersed in the liquid, in the water, to the position 15 centimeter. So you no longer expect this to be in equilibrium. You can see I tried to remove my finger, and everything is just destabilized. Therefore, what we are going to do now is to adjust. We're going to adjust this mass 100 from the 67 centimeter mark. Now, since the meter rule is falling down, you see, it's falling down to my right, it simply means I'm going to adjust that 100 gram mass inward towards the pivot, all right, towards the pivot. So let us see how we do that, okay? All right, so the adjustment has been done, and the system is back to equilibrium. At this point, the mass 100 gram has been adjusted to the point 64 point. This is actually reading 64.8. 64.8. So all we have to do is 64.8 minus 50. 64.8 minus 50. and then we'd get the value of Y2. If we subtract 50 from 64.8, you subtract 50, you are going to get 14.8, which means our Y2 for the second experiment is going to be 14.8. Once again, take note that the mass is, this mass M is totally immersed in this liquid, and like I said, it is not expected to touch the base of the beaker. Otherwise, it is not balanced. Whenever this is not balanced, let's assume you have much weight to this direction. This mass M is going to be making contact with the base of the beaker. Then you know that it's not yet balanced. Always remember, it is not allowed to touch the base of the beaker. Let me show you. All right, now you can see this. You can see, watch, this is the base of the beaker, and you can see clearly that the mass is lifted up. All right, it's lifted up. So this shows that the system is balanced, because at this position, you notice that the meter rule is still at equilibrium as it is. And this is, cool. All right. So this is just what you are meant to do. Good. So like I explained earlier, right? Like I explained earlier, now that we've gotten our first two values, the second one is 14.8. I think the first one was 17. If you work on 17 minus 14.8, if you work on 17 minus 14.8, we are going to get 2.2, which simply means if I want to get the next value, I can just simply do 14.8 minus 2.2. That of course will help me to get the next Y2 value, which of course should be 12.6. But we can find out that the next Y2 value when mass M is shifted to the position 20 centimeter, that the next value of course for Y2 is meant to be 12.6. Let us just do that to prove that once you get your first two values, take the difference. So the difference will help you to know the number, right? The value to subtract from the Y2 you just got, so that you can get the next Y2, like I explained when we were trying to get Y1. So let us confirm that for the mass M at the position 20 centimeter, the likely, all right, the value of Y2 there, once we balance up, is going to be 12.6 or thereabout. Let's just find out. So I'm going to move mass M1. Now that's the first mass M. I'm going to move mass M to the 20 centimeter mark. Somewhere here, this 20 centimeter mark, okay? Look at it. I'm going to shift it there. So you watch and see as that goes on. All right, so I have adjusted mass M to the 20 centimeter mark, right? I've adjusted it. Now I want you to watch what is happening towards this end of the meter rule. You see that I'm using my finger to suspend that meter rule now to keep it stable. If I try to bring down my hand, observe what the meter rule will be doing. It's going down, right? It's going down because I'm holding it. If I leave it, if I remove my finger from it, everything will fall down. You see what's happening? Okay, so this tells you that the system is no longer at equilibrium. So all I have to do is to try to balance up. Since it is falling towards this direction like this, you can see that I am meant to now adjust this 100 gram mass from this position inward. All right, at this point is 64.8. If you subtract 2.2 from 64.8, that will help us to know likely where this thing would balance. All right, let's find out. 64.8 minus 2.2, so that we know where to shift this 100 gram mass to in order to balance it. But remember, like I said, we are trying to prove the fact that if I actually balance up this, the value of Y2, when I take the difference from the balance point, that is, if I take the difference from where the 100 gram mass is suspended to the pivot point, it should give me 12.6. All right, so I have tried to balance it up. And when I balance that, watch this mass, 100 gram, it is positioned at 62.6. 62.6. All right, moved from 64.8 to 62.6, which was that thing I actually explained, that taking the difference between the first two values obtained gave us 2.2. If before this experiment the 100-gram mass balanced this system at 64.8, when you subtract 2.2, it brings us to 62.6. All right, and the system balances. You can see that this is the mass M. This is the mass M. You notice that the mass M is not touching the base. It's not touching the base of the beaker, but completely immersed in the water. Are you following, right? And is lifted up above the base, telling us clearly that here we are just good to go. Here is okay, as expected. All right, and look at the whole system. It is balanced. It's not falling. So this is at equilibrium right now. And it happens when the 100-gram mass was placed at what point? 62.6. Okay, now if you want to get your Y2, as usual, it's going to be 62.6 minus 50. So let us see 62.6. So let us see 62.6 minus 50. 62.6 minus 50. All right, so this gave us 12.6. 12.6, which was what I told you that we should have just obtained directly by subtracting 2.2 from the first value, that's the value of Y2 we obtained before this particular experiment. So the whole idea I'm trying to portray here, I'm trying to make clear, is that the same principle that we used when we're obtaining Y1 is the same principle that you apply here when obtaining what? Y2. At the time when the mass M is completely immersed in the what? In the liquid. All right. So remember this principle. So once you do your first and second experiment, if you don't have time, just take the difference between them and then subtract that value of difference from any of the value of y's that you get in order to get the one that follows. So this is the point. And I think from the instruction, you are meant to evaluate y1 minus y2. y1 minus y2. So once you evaluate y1 minus y2, that is the last column, I guess, of your table of value. All right. Once you evaluate it, the next thing is simply to plot your graph. You plot a graph of y1 against x, then determine its slope s1. You are also asked to similarly plot a graph of y1 against y1 minus y2, and when you plot that graph, you determine the slope s2. Then once you determine this slope, the last thing you do there, before the main follow-up questions, you are asked to evaluate the expression 100 s1 times g divided by s2, where of course s1 is the slope of the first graph and s2 is the slope of the second graph. G there is acceleration due to gravity. You can use 10, you can use 9.8 meter per square second if you so wish. So this is how this experiment is being done. Okay, so the graph follows up, and after plotting the graph, that's when you are to evaluate the expression 100 times s1 times g all over s2. The other questions where you are asked to state Archimedes principles, you are asked to draw the forces acting on the system, and state the conditions for a body being acted upon by coplanar parallel forces. These are going to appear at the end of this video after the graph work, okay? So you can just read through that and get them into your brain. I hope you enjoyed this experiment, and so do well to subscribe to this channel, turn on the notification bell so that once I upload any content, you will be personally notified. And don't forget, remember, you can become a channel member. Click on the join tab and select the GMAETS 41's platinum or diamond level. Support this channel so I'll continue to give you the best. You can also send us super thanks, okay? Below this video, you have the thanks icon there. Click that thanks icon and you can send the GMAETS 41, whatever that is convenient for you. For the job well done, as always, from GMAETS 41. Like I said, don't forget, I appreciate all of your support as you so do that. Share these video lessons to your friends, to your classmates, and invite them to join the GMAETS 41 also. If you are a Unisic student, don't forget, you can actually join us on campus, join our physical tutorials on campus, and we would still keep coaching you in order to prepare you for your first class. Alright guys, you are welcome from the live experimental work having been done. I hope you enjoyed the processes, part 1 and part 2 of the experimental method being practiced. So now we have obtained our readings. We are going to see how to analyze these readings graphically in order to see what exactly we have done in the process of this experimental work. Without wasting time, quickly, I'd like you to see display on the screen the table of values, the readings that have been obtained so far. Please watch. Showing on the screen, you see a table of reading for the determination of unknown mass using varying distances and Upthrust. We have got 5 columns there. There are 5 columns. The column for the position of M, because the unit is in centimeter. We have X in centimeter, Y1 in centimeter, Y2 in centimeter. And then, of course, as instructed, we are expected to evaluate Y1 minus Y2, again in centimeter. And you see the values we obtained there during the experiment. For example, at the position 10 cm, when mass M was positioned at 10 cm of the meter rule, you find out that the value of X obtained is 40. And then Y1 obtained is 19.5. We also obtained Y2 to be 17.0. And then the difference between Y1 and Y2, we got it to be 2.5. 5000, you know. Okay, when you evaluate stops, you report in at least 4 decimals. Okay, let us see when the position of M was 30, which actually is the last experiment conducted. Okay, position of M at 30, the value of X, as you can see showing on the screen, is 20 centimeter. Value of Y1 is 19.5. In the case where we immersed mass M totally, completely into water, we obtained Y2, and that value of Y2 was 8.4 centimeter, as you can see. The difference between Y1 and Y2 is 1.1000 centimeter. So that is the reading, and as you can see showing on the screen. Now let us proceed straight on to see what we need to do graphically, because as instructed from the manual, we are required to plot a graph of Y1 against X. So Y1 is going to be on the vertical axis and X on the what? Horizontal axis. So watch displaying the graph. Okay, now looking at this value, I decide to select a unit. That's in terms of the scale, I selected a unit that could help the points to be well spread, as the case might be. That necessitated my stretching the graph, okay? And because of the graph available to me, whatever the number of lines available for plotting your own graph will determine what you have to do. It's not compulsory to stretch. So you can see the graph as it shows. The scale that I selected in the first graph is on x-axis 2 centimeters to represent 5 units. 2 centimeters to represent 5 units. You observe that there is a zigzag something from the origin before values of x appeared, and of course you can also see that zigzag stuff on the vertical axis, the y1 axis. It simply shows that I stretched the graph. The reason why I have to stretch it is to make sure that the points are well spread. Okay. So you can now see on the y1 axis, I used 2 centimeters to represent 2.5 units. How did I actually get that 2.5 after stretching this graph? I have a video lesson that teaches you about graph stretching. I also have a video lesson that teaches you how to plot normal graph. Okay, so you can click on the info link appearing just on top and you will see the video lessons. You can take them if you do not know how to stretch a graph yet. Then, step by step, I broke down how to stretch graphs so that this graph you're now seeing, you won't have challenges in what is happening there. Alright? The 2.5 unit on that y1 axis is simply the difference between any two closest value in the values of y1 that we obtained in the experiment. Okay, if you take, for example, 12 minus 9.5, you're going to get 2.5. Okay, so with that 2.5 becomes my unit. If that 2.5 unit allows the highest value in that y1 column, which is 19.5, to appear in the graph, then we can select that and then start adding 2.5, 2.5. But after taking that difference, if the 2.5 cannot contain the highest value when fixing this unit, then of course we can increase that 2.5. But of course the 2.5, the lines available for plot in my own graph is enough. So what you have to do after stretching, the first value that will appear is the smallest value in the column you're plotting. And so you can see that, alright, 9.5 on the vertical axis, that's the y1 axis. If you add 2.5 to 9.5, you get 12.0. Add 2.5 again, you get 14.50, and then in that order down to 19.5. Then in a similar way on the horizontal axis, where you have the x values plotted, you could say 20, 25, 30, 35, 40. Alright, I also have to stretch that axis, as you can see. And the reason is, if I decide to start by saying, okay, maybe 2 centimeters represent 5 units or 2 centimeters represent 10 units, you will see that the values will be so clustered. So I decided to stretch, and to stretch it, what you have to do, like I said, take the difference between two closest value in that column that you are plotting. Like in the x column, we have 20, 25, 30, 35, 40. So take a difference between any of the two closest value, you will get 5. It therefore means that 5 units will become my smallest value to consider as unit when working on this graph. So for that reason, since I stretch, the first value to appear in the graph is the smallest value in the column you are plotting, which of course for that x column is 20. So you start with 20, you start adding the unit 5, 5, 5 until the highest value 40 appears, and that's good. So that's how that values were fixed. That's how they were fixed on the axis. So tracing the points you have, the points are clearly defined there. And what next? You are done plotting the graph. The next thing is to evaluate the slope as the examiner requires. You see, slope is change in y1 over change in x, and that gives us 19.5 minus 9.5. Then we shall divide it by change in x, which will now be the horizontal line of the slope. The highest value of that horizontal line of the slope and the lowest value of that horizontal line of the slope. That gives us 40 minus 20. Simplifying that, you'll see that the slope is 0.5. That is quite interesting. Now there is something I worked out there as notes. N equal to 100 times S1. That stuff I did there is actually used to determine the value of the N that we used in the experiment. As a matter of fact, in the experimental theory of this particular experiment M5, you have a place where it was written that N is equal to 100 S1, although in the main work you were not asked to evaluate this. However, someone might choose to do that. Yeah, you might choose to do that, no error in that. Okay, an examiner might even appreciate it, because it helps you to kind of present your work formally, explaining that N you use, you know how to get it from your experimental work. So using that formula provided from the theory, 100 S1, our S1 is already 0.5. Multiply by 100 and you get 50. So the thing is that in my own experiments, that mass N actually I use in the balancing. I'm going to show you. This is the mass N. Alright? Yeah. Normally it's meant to be covered. Like I said during the experiment, you can use something like your masking tape and wrap it. But the trick is, it is 50 grams. And actually it was 50 gram mass I used as N. So in your own experimental work in your lab, if you carry out the experiment after getting S1, if you want to actually know the value of that mass N that you use in the experiment, all you need to do is to multiply that S1 value by 100, and then you get the value. So that is that about the first graph, and I hope you enjoyed what is there and understand that. Don't forget, you can become a channel member. just click on the Join tab below this video, and then of course you can select from the platinum level to the diamond level so that you can get more benefit from this channel. Alright, and remember, if you are a Unit 6 student, you can also join our physical tutorials. Contact GMAETS 41, and of course you get the direction to our venue in order to join our physical tutorial. You also get information about what is required to join the physical tutorial. You can also send GMAETS 41 super thanks. Okay, again, below this video you have the thanks icon. Just click on it and you can appreciate GMAETS 41 with whatever that is convenient for you. A one-time support will be very much appreciated. So we are done with the first graph. We move on to the second graph. Now, in the second graph, we are required to plot the graph of y1 against y2 minus y1. You're plotting the graph of y1 against y2 minus what? y1. Now, an examiner can also ask you to plot y1 minus y2 against y1, which means in that case, you're going to take y1 minus y2 to the vertical axis and then y1 to the horizontal axis. In either case, whatever you're asked to plot, I'm following the instruction in the manual here as I have. We are actually told to plot y1 against y1 minus y2. All the same, it's just to plot the graph, and nothing is there in graph plotting. I've already told you that there are 2 video lessons that will teach you clearly everything you need to know about graph plotting. I've displayed the info link above previously. At the end of this video, I'll also make sure that the end screen displays those videos, so you can just click on the end screen and it takes you straight to those videos to take if you still have any challenge on graph plotting. Alright, so we are plotting y1 against y1 minus y2. So we are going to maintain the scale for y1 on the vertical axis. We are maintaining it. Are you following, right? And so the scale still is 2 cm to 2.5 units. My graph is actually in 2 cm. From one of the tick line to the other tick line, the graph I'm using is already in 2 centimeters. Okay? Not 1 centimeter. It's already in 2 centimeters. So we have 10 small lines between it. And then on the y1 minus y2 axis, that's the horizontal axis here, I'm using 2 cm to 0.4 units. Again, I stretched that axis. I stretched it. The reason is that the values of these y1 minus y2, they are clustered. They are clustered from what I'm saying. Are you following, right? So in order to spread them, I have to stretch the graph. And how did I determine the unit to use? All I had to do is take 2 close values, are you following, right? From that column of y1 minus y2, then take the difference. I guess when I did that, the difference I obtained was 0.4. So with that 0.4, it gives me what should be the smallest unit likely to use for that axis. All I have to do now is the first value to show on the axis will be the smallest value in the column of y1 minus y2, which, as you can see showing on the graph, is 1.10. That's the smallest value on that column. So once that 1.10 is written as the first value to appear in the graph now, all you now need to do is to start adding 0.4. 0.4 as a unit. Then you check if the lines are available for plot with this 0.4 as unit added, if it is going to contain the highest value in that column to be plotted. And that highest value, of course, you know in that column is 2.5. So when I did it, of course, it entered because my graph could contain up to 2.7. Let me assume that in adding that 0.4 as my unit to the values that I am getting, like I said, the first value to appear is 1.1. If you add 0.4, you get 1.5. If you add 0.4 again to the 1.5, you get 1.9. In that order until, if you add 0.4 to 2.3, you get 2.7. Are you following? Now, if that 0.4 that I'm adding as the unit I got when I subtracted one value from the other in the column that I was plotting, that is y1 minus y2 column. If the 0.4 as difference I got is not able to cover up to the highest value in that column, please, you can increase that unit from 0.4 to perhaps 0.5, and then you check if it will now help to contain the highest value in the column you are plotting. Alright, so let's go on. With this, the values appear as you see on the axis and both axes, and of course it is time to do the tracing. It is time to do the tracing. Now, for the first value, you see that when y1 minus y2 when y1 minus y2 is 1.10, the value of y1 is 9.5. So if you trace, clearly see, you can see it's exactly at one of that tick line point, and you have to indicate that line. You have to indicate that point rather. Alright, so you can see showing on the screen what that second graph is going to be like. And of course, you can trace the points. There is nothing about tracing points. I've actually taught how to trace and locate points in graph, okay? How to trace and locate points in graph in one of my videos actually, so you can learn more about that if you have problems on how to locate your point in graph. Alright, so all we now have to do is getting the slope of the graph, and of course, as you can see, it's showing on the right side of the graph on the screen. The slope of this guy is represented with S2, and that is going to be change in y1 divided by change in y1 minus y2. Now, if you do that, you're getting 19.5 minus 9.5 divided by 2.7 minus 1.1. And solving that, we obtain our second slope for the second graph as 6.25. Alright guys, so that is that, and I hope that you learned something from this graphical analysis. The next thing we are going to do is to go on to answer the questions that the examiner asked you to answer. And of course, while the answers are being given, they are going to be displayed on the screen. We shall round off this experiment M5 formally now by looking at the last part of the questions in what we are expected to answer as questions. Alright, as the answers are being given, you would see them appearing on the screen. Okay, so the first question, we are asked to state the conditions of equilibrium for a body acted upon by a number of coplanar parallel forces. Now, there are simply two conditions to that, and we're going to learn this condition now. So, number one, the algebraic sum of forces acting on the object must equal 0. Now, that statement, alternatively, we can say that it means the sum of forces acting in one direction equals the sum of forces acting in the other direction. It's the same as that statement already made. Okay, now the second condition is the sum of clockwise moment equals to the sum of anti-clockwise moment. That takes us to the next one. Alright, the next one actually is with the aid of a diagram, indicate the forces acting on the meter rule in the experimental setup above, figure M5A and figure M5B. Now I would like to answer that question lastly because I'm making use of the board for that, okay? To draw the forces acting on that object, that is on the meter rule during the experiment. So let us move on to the third question, okay? We are asked to state Archimedes' principle. Archimedes' principle states that when a body is totally or partially immersed in a fluid, it experiences an upthrust, which is equal to the weight of the fluid displaced. So that is that. Precautions taken during these experiments in order to ensure accurate results, right? I ensure that the masses are carefully suspended at the required position before taking the reading in order to obtain accurate values of x and y. That is x and y1. Also, I ensured that the masses are stable to avoid destabilizing the system before taking readings. The third one, I ensured that the mass M in the second experiment is completely immersed in the liquid and not touching the base of the beaker before taking my readings. I kept emphasizing on that during that second part of the experiment. That mass M, totally or completely immersed in the liquid, should not touch the base of the beaker. Otherwise, if it is making contact with the beaker, it means you have not attained equilibrium yet. Number 4, I avoided errors due to parallax while taking readings by looking directly perpendicular at the balance point. Yes, very important. If you are taking reading from something, you don't look from side. Look straight on to that thing, perpendicular. Your eye should be connected straight on to that thing. If you are reading that thing downward, then your eye should be facing downward like this, okay? You don't take reading from side like this, otherwise there will be some kind of interference in values on that instrument you are reading, and of course it is going to cause what is called error due to parallax. Then also I ensured that the meter rule is properly stable by allowing a little time after adjusting the suspended 100-gram mass so as to take reading. So these are various precautions taken during the experiment so as to ensure accurate result. Good. Now I'm going to draw on the board the forces that are acting on the meter rule during the experiment. Now let us look at the forces that acted on the meter rule, okay, during our experiment. Going to be fast in trying that. So for the first experiment, that is figure M5A. We have this is the meter rule. This is the meter rule, and then the pivot point, okay? The pivot point is an upward reaction. The pivot point is an upward reaction this way, which I'm going to use R to represent. Okay, I'm going to use R is a force upward where the knife edge was supporting the meter rule. And then of course the meter rule has its own weight towards its center, so I'm going to use W to represent it. Alright, that's the weight of the meter rule. And of course you remember that from one end we suspended a mass, so we suspended a mass here. Let's take this as weight of M, weight of mass M, alright? And then here we have another mass. This we're going to call it the weight of that 100-gram mass, okay? The weight of that 100-gram mass. So for that first experiment, this is what we've got. Like I said, our R is reaction force. You can actually define this for your examiner, where this would be the force due to mass M. Are you following? And then this is the weight of the meter rule. This is the force, all right, due to mass 100 gram. Like I said, this is for the figure M5A. And then for the second experiment, it's going to look like this. Let this be the meter rule. Let this be the meter rule. And once again, it was pivoted. I can just start by even showing the weight of the meter rule, which usually acts at the midpoint, okay, the center of mass of that meter rule. I'm using W to represent it, the weight of the meter rule. And of course, that is also force. If you want to label using F, the choice is yours. Now, it was pivoted. Let me show here to be the pivot point, and this is the reaction force where it was pivoted. Now let us take this to be our weight of that mass, that was immersed completely inside that water. Now at this point there is an upthrust. There is what I said, an upthrust. So just directly upward, I am going to permit me to use U for it. Let me use U for it, where U is upthrust. Then on this side, I have my 100 gram mass. All right, so this is for figure M5B. So these are the forces acting on that meter rule. So guys, that's all about this experiment M5, and I hope you've learned something greatly from this experiment. The truth remains that the principles applied here, you use them in many other principle of moment experiments where you balance meter rule, light following right on a knife edge, as the case might be. It's alright, I'll be seeing you in the next video, and until then, remember to take your studies seriously. Don't forget, please, to support GMAETS 41. Your support as a means of appreciation of what GMAETS 41 is doing. That support is also greatly appreciated by me. Is that okay? And of course, GMAETS will continue to give you the very best. And don't forget that code, right? That code number 41, telling you that here you excel and nothing stops you, okay? You excel. I'll be seeing you in my next video, as I said. But don't forget, the two videos I talked about. Are you following? That will guide you step by step on how to plot graph and even trace your point. Click on these end screens and they'll take you to that video lesson.